Troy and Matt, thank you so much for inviting us to join you this afternoon. And Troy, I have to tell you, you're a tough act to follow. I literally can't think of one song I can remember a phrase out of, much less the whole thing. That was very impressive.
Well, tell us a
Well,
little bit about yourself, Jim. I'm going to pull up the website. We're going to get to that video that you guys like to show. Just kind of everyone's minds get wrapped around the logistics of literally heating up a reservoir, flooding it with nitrogen. How does this look? But while I'm setting this up, please tell us a little bit about yourself, specifically how you became the king of nitrogen flooding.
well, I don't know that we're there yet, Troy, but we're certainly working in that direction. My name is Jim Landry. I'm from Lafayette, Louisiana. I was the former Director of Advanced Materials for the state of Louisiana under the Department of Economic Development. I'm also the owner of a company called Thermal Mitigation Technologies, which is a polymer chemistry company focused on flexible epoxy resins, primarily for oil field applications. I'm also a member of Plasmera Energy, which is why we're here today. Under my capacity of the Director of Advanced Materials, we ran across a technology that was very intriguing to us, although it was being used for a totally different purpose. We ran across a technology that was developed essentially to heat water in the form of a boiler. And so they would bring the water up to slightly less than 200 degrees Fahrenheit, essentially for hot water. So we began to look at the technology and see what we could do by increasing the energy, thereby increasing the temperature of the water and bringing it all the way to steam. When we tell people that we had set out to develop what's generically referred to in the industry as a downhole steam generator, I get the same response. Oh yeah, downhole steam generator, cute little oil field device. You put it down the well and but Jim, there's no such thing as a downhole steam generator. And again, we would get that response from practically everybody that we talked to.
That's a perfect segue. Yeah. Let's start this video. So I'm going to share my screen, and then Jim, if you have any commentary.
But essentially, all of us are familiar with surface steam technologies used quite a bit in Canada. This is a depiction of a surface steam generating outfit. You can see the once through steam generator here in the background. And all of this other equipment and build out is essentially to clean water. And then once they create the steam, then they pump it down pipelines that can be many, many miles long. We've seen them go over mountains before it finally gets to the wellhead. And of course, on its way to the wellhead, you lose quite a bit of temperature, both in the exhaust stack, and then literally every 100 feet that you travel, you're going to lose heat. Then of course we lose heat to the well bore as we go down. So what you end up with is a very inefficient steam. You may have 15–20% steam by the time you get there, as opposed to our thermal fluid generator, which we generate literally yards away from the wellhead. And it's done in a very small compact system. This is a representative of about a 40-foot trailer. You can see the trailer being pulled by a 1-ton pickup truck. The white box at the front is a computer control room, although that's not always necessary. So a very small device that we bring from well to well to well. And our initial intention is to do what Matt mentioned earlier, which is huff and puff cycles of injecting steam and nitrogen into the well bore for about a 3-week period of time. And then here, what we're showing is in a downhole application where we would lower the tool to the perfs with the thermal packer on top. And then we have our feedstock, which is electricity and nitrogen. You can see the little lightning bolt, if you will, when we have the nitrogen that passes over this area. It generates a tremendous amount of temperature and also velocity of the steam. And we use the nitrogen to both create this energy, but also to be the carrier gas, if you will, to help drive the steam into the reservoir and overcome the reservoir pressure, more importantly. So what Troy is showing you now was an actual field run um, where we did high pressure or higher pressure than what we normally do. So we had essentially an air compressor to produce a volume of air, and then a booster compressor to take that volume of air and bring the pressure up to about 200 PSI above reservoir pressure. And then we inject either from the surface or downhole, as the animation shows, um, nitrogen gas that we bring into the device. It's actually split so that we have a small volume of nitrogen at relatively low pressure, goes into the heating chamber itself and creates all of this temperature. And then the majority of the volume of the nitrogen remains cold, and then it's rushed around the ID of what we call the shroud and the OD of the heat chamber. And so the nitrogen gives us the velocity and the pressure that we need to overcome the reservoir pressure.
Wow.
It mixes with hot gases, hot nitrogen gases that escape out of the heating chamber, and they escape at temperatures literally about 20,000 degrees Fahrenheit. So essentially what we're doing is we're creating steam and gases that are entirely too hot to put into the reservoir, and we mix them with gases and water that is too cool to put into the reservoir and be effective. And so what we have essentially, to kind of dumb it down, is a very
My
sophisticated,
dumb brain can't handle this kind of stuff. I need it.
I assure you there'll be questions. I'll have to say the same thing, Troy. We'll have to refer it to the experts. But in a nutshell, what we have developed with our thermal fluid generator is a very sophisticated shower valve. And so we have temperature pressure sensors that are mounted at the bottom of the device if it's downhole, and up at the wellhead if we're steaming from the surface. And it's constantly measuring the real-time temperature and pressure of what's happening down at the bottom of the well and into the perfs. So that if we start generating more temperature than we would like the reservoir to be exposed to, or it's creating more pressure than typically the Department of Natural Resources would restrict us to, then the device is going to alter the performance of the machine so that we get back and stay within those parameters.
Skippo, remember when we talked about having an oil knob? We're like, we just need the field engineers to go out there and turn that oil knob.
Man. Turn up the oil. That's all you need.
That's what it reminded me of. Jim, please pull up the presentation that you have, share your screen with the audience. And I want to remind everybody that the video that we just watched, at least from my perspective and what I saw, is that logistically, they create steam to get this process happening a lot closer to the wellbore than we currently do around the country. So if that alone could be an economic increase to make this feasible, then let's talk about it. That's a good idea. And that cartoon really helped me just to realize, like, wow, you have these facilities, it looks like a big old doghouse thing that people like live in. I don't even know. And it's steaming, and that thing looked like a multi-$100,000 facility. And you're cruising in on a pickup truck, just hitting speed bumps, no problem at all. Just bring it right to the wellbore, turn this thing on, and oh, by the way, what do you need exactly? If we need to dial some things out and make it more efficient and more productive, wow. I mean, that's good.
I can address the audience. So we got a really good question from Mr. Brian Bottoms. So he's asking, when you do these steam floods, are you using only fresh water, or do you have the capability of using brine as well?
Oh, it's an excellent question, Brian, and we get asked that a lot. As you can imagine, we had some champions of our development of our technology in the very beginning days, primarily out of Canada. And one of the major heavy oil companies up in Canada basically told us, if you can't use produced water, our level of interest is not going to be as great.
Wow.
And the way our device works, using produced water has really no detrimental effect to our tool, because the steam
That's
is
awesome.
actually manufactured, if you will, once it leaves our tool. As hot as we get inside the heat chamber, the actual conversion of the water into steam occurs in what we would call the flue gases. In this particular case, just the hot nitrogen to combust the water into steam. However, having said that, if you're using produced water, you're going to have magnesium and calcium carbonates that are going to drop out of the water. Essentially, what we end up doing is, there we go, Troy. Thank you so much.
Yep.
Is we're thermally softening the water, and so could we do it? Absolutely. It would have no detrimental effect on our technology, but the sediment that would be left could clog the ID of the piping system as it goes to the perfs, and could conceivably clog up the perfs. So a better solution, we think, Brian, would be to add another thermal fluid generator or two, and thermally soften the water before it gets to our tool, so that we could literally use the produced water, but we would want to treat it ourselves as well, so that it doesn't affect the production of your oil well, not so much our tool. We've run the tool on some very dirty produced water just to go through the
Wow.
exercise. As a matter of
Wow.
fact, the produced water was so oil laden that you could see it adding to the energy of the device, because we were essentially burning the oil in the water.
So
Well,
I
so,
think,
oh,
go
oh,
ahead,
I,
Skips.
I was going to say, we have one more question from the audience. Do you want to do this prior to the presentation, or do you want to do it after the presentation, Jim?
Sure, or even just
We're
doing,
doing good
Matt.
on,
You're welcome to interject anytime. So
yeah, we're
Perfect.
doing good on
Perfect.
time.
So this one's from Molly, and she says, any thoughts on fractures in the system maybe acting as quote unquote steam thieves, or natural or hydrofracks? And then she says, this is an awesome technology, by the way.
oh, thank you, Molly. And I really appreciate the question, because you guys make us think. We've had that question before, and I don't really know how to answer it other than to give you our honest answer here. We don't know that we're going to have any effect or any fracking ability as a result of the temperature. We could as a result of the pressure. So typically we would think we would not be fracking the rock, the reservoir. However, your point is absolutely valid, and I very frequently describe it as trying to fill an inner tube with air when it's got a hole in it. And that's what Molly is describing. And so some of these older reservoirs, and we're looking at fields that are, were drilled in the 30s and the 40s, and many other enhanced oil recovery techniques have been attempted, and they'll sometimes cut fingers in the reservoir. And so just like an inner tube, we can pump all the nitrogen and all the steam that we could possibly muster. If the inner tube is not solid and has a hole in it, you're going to lose some of the efficiency. You'll still warm the oil, you'll still build up some pressure, but you're going to lose that pressure more quickly than if you've got a good homogeneous reservoir without any fissures or substantial cracks in it.
Well, interesting. Obviously, the video and the conversation up to this point has got us really further than I thought it would be. I mean, we're really talking about a fracture network in the reservoir. We're talking about how this stuff is actually moving. And so I think what I would love to pull out of this conversation, I think it's obvious that the logistics make more sense. It's more efficient. I think that's to go without say at this point. I'm definitely interested on the technical side of doing this. So how does this tool actually get down into this reservoir? How is it is it flooding through these perfs and things like that? Ultimately, a case study was the goal, but you guys talked about how a case study is what everyone gets if they want to further investigate in this technology. So you guys have the resources, the case study that shows what happens when you do this to reservoirs, and it's from what I could tell in conversation leading up to this, it absolutely works. It has something to say, and it just comes down to the economic situation. And so that's up for them to decide. But for now, I think that's it. Let's look at this thing downhole. Let's talk about the concept of, you have a temperature gradient, you have structure, you have all these things that could have an effect on how this tool responds and how it holds temperature, and how efficient really is this tool, Jim?
Well, I wanted to say one other thing, Tamale, to further answer Troy's question here. If we have a reservoir that has been fracked, we think it's a wonderful ancillary technology to work with, because for us, it's all about surface area. So the more surface area that's exposed to the hot gases and to the steam, the more effective we're going to be. The quicker we're going to add both pressure and temperature into the reservoir.
Wow.
So excellent question, Molly, and we'd love to share some more thoughts as well as hear yours in the future. What we do, Troy, when we put the tool down hole, and again, in our previous conversation, we have been looking for what we would call, the shallow fruit, the easy pickings. So we've been looking at relatively shallow, to this point, heavy oil wells that we did not have to put the tool down hole. When we get to about a 2,500 foot depth, then you're going to start losing steam efficiency, and you're going to want to lower the tool down to the perf area. And so what we would do, we have to have an umbilical of coil tubing strings that feed the tool with electricity and nitrogen and water. And so to do that, we need those different size coil tubings on a flat plane. So the company that manufactures and runs the flat plane device, the coil tubing device, lowers into place a thermal packer, sometimes two of them, one at the bottom, one at the top, depending upon the conditions. And then we stab the top thermal packer with the tool, so that the actual heat source, the combustion chamber, if we're using a combustion system, or the plasma torch, if we're using plasma, remains above that bottom thermal packer. And then we have a tube essentially, and you saw that probably in the animation, with a slotted liner, and that goes below the thermal packer. And so we're creating the heat and then injecting the steam below that thermal packer. And so we're essentially trapped in between two thermal packers, or a top thermal packer and the bottom of the well bore. And so the steam and the hot gases have no place to go but into the perf.
And so it's just to interrupt, Jim, unless you wanted to jump to another page, I wanted to talk about the idea of coming at this from a hydrothermal geology model, and the fact that kerogen is a universal kerogen, and this kerogen is coming up through a system, through these deep fractures that are the plumbing system to our reservoirs, and it's coming in hydrothermal conditions. And the Lewin paper that we discussed, and that's available at our website, he did it in the lab. He created a hydrothermal process in the lab. He increased temperatures drastically, and then he started messing with the brine. He started pumping in things like nitrogen and things like salt, and he started making the brine chemistry change. And what his results were, and this is a 1997 paper, his results were, as it got saltier, it produced more light hydrocarbons in this reservoir. So there is something, when you change the viscosity of this hydrocarbon and you flood it with nitrogen, there is a new concept in town that says, wait a minute, what is actually going on here from a hydrothermal perspective? How are you actually manipulating this system, the hydrocarbon chain specifically, and are you actually building some in this process? As you increase temperature and flood it with nitrogen, what's actually starting to move from the brine to oil and back and forth? What's actually happening? I love that also you talked about, obviously heavy oil is the goal here. So Canada, California, that's a prime place for this. Even South Texas. I mean, there's places that have heavy oil stuff. So we are familiar with places that this probably could be applied immediately. But I'm sorry. So that got me sidetracked, Jim. Please continue.
Solid rant.
No, that's very interesting premise, Troy. And it's all things that we are fascinated with and we want to experiment with. we just had a collapse of the oil business, and it kind of stopped a lot of that exciting work that we wanted to do. But it's interesting that you talk about the salt water, because we do have issues where in certain reservoirs, you have certain fines or clays that essentially will swell on you if you interject fresh water into the reservoir.
Right.
So our choices are you avoid that reservoir, or you use salt water to make the steam. And because we can generate so much temperature in this device, we can make superheated steam where you would have virtually no moisture left in the gas, or we can do saturated steam, which means you have some droplets, water droplets, mixed in with the gas. And that was our way of dealing with the produced water and in fact the salts in the produced water.
I love
so that if we get 85% saturated steam, for instance, then you're going to have some salt water that's going to drop out more readily, still in its soluble form in that 15% of the water. And again, all things that people have talked to us about, we learned far more talking to other people like Brian and Molly than we have, on our own. That's why these things are so beneficial, and we love to hear all of the questions, even though sometimes our answer is going to be we don't know until we do it.
That's a good answer, Jim. That's a good answer. All right, you're asking the right questions. Can we confirm, either Molly or Brian, at this time, can we confirm that you have stable Wi-Fi, that you got some noise cancellation headphones, and you have video? Because I want to bring you in, and I want to really talk about the economic implication of this as an operator in the unconventional play through Molly, or as Dietering's finest geologist, Mr. Brian Bottoms. Are you seeing this as being an actual tool to be used? That's my question to you guys.
Brian says he doesn't have noise cancellation headphones, but
how quiet is it in his room?
Are you in a quiet room?
And what about Molly?
It's just you. Okay. Brian is giving us the thumbs up.
All right. And Jim, are you okay with that? Can we stop sharing the screen? Okay, let's jump into a conversation. Are we live with Brian Bottoms? Let's bring him in.
Yeah.
How's it going?
Welcome back, man. Last time we talked was ERTEC 2019. You talked about the Anadarko Basin. That's one, and I know you're counting. The Anadarko Basin was exciting, man. There were some crazy anomalies, especially with the Woodford. Why is the Woodford producing oil at incredible depths? That's odd. That's an anomaly. Let's talk about it.
Yeah, I mean, you want to talk about the Woodford or about EOR, I guess.
Yeah, no.
Let's stick with the subject. Yeah, we'll stick with EOR. Don't listen to Troy.
Yeah, I guess. I mean, yeah, I do see EOR though as having immense applications going forward. I'm not as familiar with steam flooding, and so I thought this was very interesting. And I guess for that same matter, I'm not as familiar with nitrogen flooding. I guess a lot of the floods that I do encounter are either CO2, water, or polymer floods. But all of them, excellent capabilities of boosting recovery and definitely have a time and place.
That's right, man. And thinking from your perspective, everybody's been talking about how the frac hits are such a problem. Well, maybe those frac hits from this perspective is actually a plumbing system. And if you actually have some good control through microseismic and everything else we have, and the technology we apply to actually figuring out how the fluid is moving through this block of rock that brings us a bunch of efficient energy we call hydrocarbon, can those frac hits actually be turned around and be a positive thing through some technology like this, Brian? That's my question to you.
Oh, yeah. I mean, I'm definitely in favor of pressurizing up offset wells before you frack them. Either load them up with brine water or just shut them in and let the pressure build. I think a lot of people see positive responses when they do that, in terms of being able to bring the well on much quicker, and as well as just mitigating any frack hit downtime and production offsets or bad production profiles that arise due to frac hits.
Right. No, this is very interesting. And really cool is the idea that you can take your produced brine. So this thing that operators just simply have in their LOE, a lease operating expense, every dime that goes into making profit into this lease, one of the major things, especially in the unconventional play, is what are we doing with all this brine? This is very inconvenient. We got to drill a 15,000-foot vertical well or whatever it is to get rid of the brine. There's incredible technology coming out about that. Can we simply turn it around, turn it into steam, increase recovery?
Yeah, Brian, and you brought up a very interesting point when you talked about CO2 and some of the other methodologies of doing these floods. We use nitrogen. We could have used any one of a number of other industrial gases. They all do the same thing. The performance of the or the end result of the technology is somewhat different in that the different gases have different enthalpy ratings. And so what we're trying to do obviously is try to transfer the temperature that we create into the oil. The reason we chose nitrogen is actually several-fold, but we didn't want to do anything that was so exotic, Brian, that people that were in the oil business would say, hey, what do you mean you're gonna do this process and heat up helium gas, for instance, that's very expensive. You couldn't afford to do it at $40 a barrel oil. The thing that we probably didn't spend enough time on the animation is we're in total control of our feedstock, which includes the nitrogen. So we have two basic feedstocks, one being electricity, which we generate ourselves with a diesel-driven engine electric generator. And then we have a nitrogen membrane compressor. So we're taking air in from the atmosphere. Approximately every cubic foot of air has 80% nitrogen, 20% oxygen. And we're separating that and sending the oxygen right back into the atmosphere. So while the nitrogen isn't cheap, it's the cheapest industrial gas that we could use for this application, and the oil business uses it every day. You know, we're constantly repressurizing reservoirs with nitrogen, and one of the other benefits of nitrogen is it's chemically inert. We don't have corrosion problems. It doesn't participate in combustion in the event that there were some sort of a fire or something down in the reservoir. We would actually be helping to extinguish it. So we chose nitrogen for that reason. And then what we're trying to do, Brian, is we're trying to affect the two major components of the Darcy law, being temperature and pressure. We generate a lot of thrust, if you will, right outside of the torch, but it doesn't equate to pressure 2,000, 3,000 feet below the device. And so what we need is a carrier gas, and that carrier gas we use is nitrogen. And then as you alluded to, there are circumstances where nitrogen is miscible with steam, just like CO2 is, but it's more difficult to make it miscible. And the pressure conditions typically mean you're going to be in a really deep well for the nitrogen to become miscible. So we're simply using the nitrogen as our carrier gas, and then it becomes warmed. You've got a small volume of nitrogen coming out of the torch that's literally 20,000 degrees Fahrenheit, and then a huge volume of cold nitrogen that's tempering that 20,000 degree flame and bringing it down to 375 to 450, somewhere in that range. And then of course you're injecting water right into the corona, which looks like this big hawking flame, but it's literally the energy that we create by disassociating the molecules of the nitrogen. And it becomes very turbulent.
Molecules of the hydrogen. Wow, that's a term. What is your tool looking like? Can you dial that in so you're just boom, 130 degrees C, nitrogen flood this thing and see what production does?
You can dial it in very easily. This is the control panel. We use a PLC control panel, and the screen sort of looks like a microwave oven, and you can program anything you want.
Nice.
But in fairness to your question, Troy, steam is also reflective of downhole pressure. And so at some depths and some pressure, it's going to take you more energy to make steam.
Right.
And you'll reach a depth where you're just going to be making really hot water, but it's not going to be as efficient as steam.
Right. So
So
how's the science?
Oh.
Sorry to interrupt you. Go ahead, Skips.
Another question from said audience. Brian, do you have anything else you want to add, or any
I can take
final
it
thoughts?
offline, but it's kind of unrelated. But what do you think about the effectiveness of just using straight up methane, and if say in a place like the Delaware where you have takeaway restrictions on gas, just putting it right back in the reservoir? Do you think that could be effective as well?
I think it's a wonderful idea, and certainly better than flaring gas, or if you don't have a market for it. Yeah, we're like
That's
I say,
huge.
Brian, this is the second generation of the device. The first generation of the device, we were using a combustion system, same principle, but a combustion system, whereby we were using the natural gas as a fuel. Now, in the second generation of the device, we don't need fuel, but in the first generation of the device, we would use natural gas and compressed air as an oxidant. And we're literally talking to a foreign country who shall remain unnamed. They're flaring literally 70% of their gas. And so what we're talking to them about is, if you truly don't have a market for the natural gas, let us burn it in the first generation device. And the reason we're saying burn it and re-inject it as opposed to just re-injecting it, number one, at a minimum, I would re-inject the natural gas. But at the same time, if you had no market, we could burn that gas. It's a 10-to-1 air to fuel ratio for us to be able to promulgate a flame and keep it going. So 1 million cubic feet of natural gas becomes 10 million cubic feet of flue gases. And so for that 1 million cubic foot of gas cost, you're going to be injecting 10 million cubic feet of flue gases, hot flue gases, into the reservoir for your pressure maintenance. And so what we're doing, I call it by serendipity. It's the way our tool has to work. But you're both heating up the oil and lowering its viscosity, and you're increasing the pressure in the reservoir.
Right. Wow. Brian Bottoms, sir.
Well, thanks for having me, guys.
Love you, man.
Yeah.
Later.
Thanks, Jim.
Thank you, Brian. Pleasure to meet you.
And Skips, you got somebody else that wants to jump in?
Yeah, we have a couple other questions in the Q&A. So this one is from Wiley. Is this for stripper wells or heavy oil wells, or both? I think we kind of answered some of that, but do you have
all of it? Have
you done any work in stripper wells in the meantime?
Yeah, that's really all we've done so far. We haven't really, we haven't come across a potential partner that, is producing 300, 400 barrels of oil a day, and he wants to bump up that production. So what we're typically seeing is two barrels a day, 3 barrels a day, that we increase to 15 barrels a day, 20 barrels a day, and sometimes, higher than that conceivably. But yeah, so it's our initial appeal, I guess, the way to say it, Matt, is for these stripper wells. And yet this one group that we're talking to internationally, they have prolific production rates for heavy oil, but they tend to peter out in a relatively short period of time, primarily because they lose their gas cap.
Okay, man, that's great news. I really like the kind of going into detail as far as the application of using that natural gas that, otherwise would be getting flared right now or sent to Waha. People are actually paying to have their gas sent to Waha, and it's just all we know is just going up, and they're flaring it there. But I mean, that would be awesome if we could potentially use that gas to charge up some new or some older wells that had been, quote unquote, the huff and puff method again.
Yeah, absolutely.
So not the 400, 600 barrel a day wells, the horizontals that are producing fine. If you think that's good economics and you don't want to mess with that system, you don't want to mess that up, then go to the well that's been producing for a year and now it's at 10 and a bunch of brine. I mean, that thing's losing value. That is the target.
Yeah, exactly. Right. Because that's the biggest problem, right? Is like we have these decline curves. People are messing with those B factors, and all of a sudden it's like, oh, this well was supposed to be producing this at the end of the year. It's not. Now we can go back in. We have this resource, this extra produced gas, and now you can huff and puff these other wells and get them stimulated again.
Dude, are you kidding me?
So, and you see the other option, Matt, is if you've got that readily available gas source and it's a good quality gas and it's near enough to the well bore then you can use the combustion system or the plasma system. It doesn't really matter. The reason we chose and still prefer the plasma system is because when you go to the next well, then there goes your close proximity to your gas source. So then you have to start running small pipelines to bring your gas from well to well to well to well. With the plasma system, we created at the wellhead.
Wow.
So we that's really where the true cost savings comes in.
You got economic options.
Yeah, absolutely.
Economic options. Skips, do we have another daring guest that wants to ask a question or even come on stage?
I think I gotta go back through the.
And A-Train's running this too. So I like that. I like what you're doing there. I see your finger every now and then hit the screen. But man, I still like what you're doing.
It's the phone. It's the phone. It's the only way it could be done.
Let's go.
Don't judge my disgusting fingers.
No. You check it out. You see if there's anybody else that has a real pointed question. And so just to recap the presentation, and we can be wrapped up in probably 5 minutes or so, Jim, unless we get another one to really strike this off. This obviously traditional method, costly.
Okay.
Plasmera enhanced is changing the game.
Yeah, we got one more. So I'm going to botch your name, and I'm so sorry, but this is from Yadir, and he's asking, what types of volumes are you talking about as far as injecting nitrogen into a reservoir?
The current design, or our target, is to produce the equivalent of 5 million BTUs of steam per hour. And so we're essentially in that size unit producing about 900 SCFM gas per minute of nitrogen. And again, part of it goes into the heating chamber. The vast majority of it goes around the heating chamber, but they all combine. So roughly about 1,000 standard cubic feet per minute. Now, if we're going to put the tool down hole, it has to fit down hole. And so if we're working with a 7-inch well bore, for instance, the OD of the tool is 5 inches. But if you're in a shallower environment, or we're not as focused on heating the oil as we are reinvigorating the reservoir by pressure, then we can build as large a unit as we need to build on the surface. And so you could increase that gas injection considerably. In a downhole operation, you're limited obviously by the size of the oil well itself.
Cool, right on. Jim, do you want to touch anything else on the presentation before we wrap this up? And obviously this, and we believe, truly has an impact on the bottom line currently in the industry at today's value and at today's dollar. Like we absolutely are pushing forward with this. It's fascinating, absolutely fascinating, especially with the new geologic concept of hydrothermal geology and what Lewin was doing in the 90s and at the lab. You guys are doing this at reservoir, well above the generation model, right? Where it should be generating. This rock's sitting above where it was potentially generating. So now you're going back in and you're just bumping it back down, essentially, if you want to just look at it as a simple idea. So one last few minutes. What do you got? Anything you want to show on the presentation before we?
Well, I'll just say this, Troy, you were talking about projecting increase of production by stimulating the reservoir in this type of a manner. There's been some wonderful computer science that's been developed that if we give them accurate information about the reservoir, then they can change in their logarithm, essentially, the pressure and the temperature. So just as you were saying earlier, Troy, if we show them that we can increase the temperature in the reservoir by 10 degrees, 15 degrees, and we increase the pressure by 300 PSI, 1,000 PSI, they'll give us a relatively accurate, educated estimate as to how much more oil production you're going to get out of the ground. So we think our new technology, in collaboration with a lot of other new exciting technologies, is very exciting.
It is. I agree. Skippo, you got any final thoughts before we let Jim go and bring on our sponsor for the show?
Dude, I think that's a great way to start the show. I think, I'm good. I think the audience had some phenomenal questions, and yeah, they're thanking you, Jim. They
Well, thank you
appreciate
so
the
much,
time.
Brian. And Molly, great questions. We really appreciate you both.
Awesome, Jim. Okay, I'm going to transfer you from panelist back to attendee. Please stay in attendance. Your experience specifically is changing the game today. Well, let me restate. Your experience today is having an effect on how we change the game in the future. And it's all about the investment of today and the idea that it's to make a difference in the future. It's not an instant gratification thing. We're not there. We need time. Everyone needs time. Your experiences, I hope you stay for the rest of the show. And we certainly, we're honored to share the time with you, sir.
We will, Troy, and thank y'all both so much for inviting us to participate. And we absolutely want to have an impact on the future of the oil business. We love this business. We've been in it our entire careers, and we want to do everything we can to see it grow. And it's going to grow by new and exciting technologies, and we just want to be one of them.
That's right. And new ideas. All right, Jim, we'll see you.
Thank you, guys. Thank you both so much.
Let's go!